Now that we finished talking about detection, let's talk about estimation. And in this video, we'll talk about three different kinds of estimators, ML, MAP, and something new we'll introduce called MMSE. And we'll talk about what those acronyms mean in a little bit. So probability is also an excellent foundation for making inferences, right? So we saw before in detection theory how to make decisions. So we're going to make inferences here from partial, noisy observations. And this is known in the literature as estimation theory. So you're trying to estimate something, or statistical inference. You're trying to infer some value. The key idea here is that you're trying to understand or estimate a set of unobserved random values, right? Random variables. And you have the values of another set of observed random variables, right? So that's kind of the trick. You're trying to go and use one of these to predict the other. So one example might be that you're trying to find the location of a target based on some radar measurements. Okay? Another might be trying to estimate the heart rate of a patient after you've made some electrical measurements, right? So you've maybe hooked them up to some kind of EEG. And another might be you're trying to identify the model parameters of an aerial drone, right? So you're trying to come up with a good model for this vehicle based on some flight test data, right? So these are all engineering applications where estimation plays an important role. And in this video, we're going to start with the scalar case where you only get one observation, and we're going to do that to build intuition, but you quickly see that the main ideas here can be extended to many observations for prediction. And in general, you might want to predict or infer many things from your many observations. All right. So let's talk about the framework for scalar estimation. So the first thing that we're going to have is a prior distribution, okay? So a prior distribution is just going to be the marginal distribution of our unobserved random variable, okay? So in this context, we're going to call the unobserved random variable x, all right? That's going to be our notation. In the discrete case, it'll have a marginal PMF, and so the PMF is Px of x. And in the continuous case, it'll have a marginal PDF. So we'll assume we know what that is. Okay, and here's an illustration of a possible continuous random variables PDF. We're also going to have an observation model. Okay, so this is how we collect our data about the thing that we care about. We don't observe it directly, but instead that's passed through a conditional distribution, and it generates some observed random variable. Okay, so we're going to see y, and y is what we're going to use to try to predict or infer x. In the discrete case, so where y is discrete, we're going to see the conditional PMF, p of y, given x. And in the continuous case, we're going to see a conditional PDF. Okay, our conditional PDF is going to be f of y given x, and we're going to know this model. So here's an illustration in green of a conditional PDF, okay, assuming that y is continuous. All right, and finally, we're going to have to come up, so these two things above are things that were distributions that we're going to be given at the outset, all right? And our goal will be to come up with an estimation rule or an estimator x hat, which takes in y, and it outputs an estimate of the unobserved random variable, in this case x. Okay, so that's the thing that we actually care about, but we don't get to observe it directly, so we have to use y to make an estimate x hat. And so we have this estimator, we take the value of y, we put it inside the estimator, and then that produces our value x hat of y. Okay, so recall that we were using before the probability of error as a measure of performance. Okay, so that's what we use in detection, whether you're right or wrong. The problem is in most estimation contexts, our estimate x hat will never be exactly equal to the true value of x. So in these cases, what that's going to mean is the probability of error is always going to be 1 because we're never equal to the true value. Okay, so this isn't a good way to compare estimators because they will all fail with probability 1 to get exact equality. So we want some other kind of measure. There are many you could choose from. Here, we're going to focus exclusively on mean squared error. All right, so what is mean squared error? Well, we denote it with MSE, and all that means is you take the true value, subtract your estimated value, square it, and take the average. Okay, that's the MSE, and this x minus x hat is called the error. So it's the squared error on average, the mean squared error, MSE. And the other thing we might be interested in is the bias of our estimator. Okay, so this is a term that basically captures whether on average our estimator is giving us the true value. So we'll say that x hat is unbiased if the error has zero mean. Okay, and what you'll notice from this is what it means is that x hat has to have mean equal to the mean of x, meaning that on average it is returning the correct value, even if it wanders around it randomly. Okay, so as a starting point, let's go back to the ideas we introduced in detection. Think about what it means to have ML and map estimators, right? So we figured out what it means in detection. What does it mean for estimation? All right, well, the maximum likelihood, or ML estimator, x hat ML, it takes in y, and then it tries to select the value of x that best explains the value of y that you've seen, so the highest likelihood value. So in the discrete case, what you're doing is taking the argmax of the conditional PMF of y with respect to x. So you wander around the range of x, and you try to find the x that gives you the highest value of this conditional PMF once you've plugged in y. And that's going to be your x hat. In the continuous case, you're going to do the same thing, except you're just going to wander around plugging into the conditional PDF. Okay? So that's your ML estimator. The map estimator is going to do the same thing to the maximum a posteriori, or map estimator, x hat map. That's going to do something which seems a little better. It's going to select the value of x that's most likely given the observation. At this point, I just want to remind you that in the detection context, this was the optimal thing to do if you knew the full probability model. So if you know the probabilities there of the hypothesis and the conditional probability model, this was the best thing to do. Here, it will turn out that it is not the best thing to do. And we're going to see why in a little bit. But let's just look at the form of this rule. So if x and y are both discrete, you're taking the argmax over x, and you multiply the conditional PMF of y times the marginal PMF of x. And it turns out, by Bayes' rule, this is the same as taking the argmax of the conditional PMF of x given y, right? Because you could just divide this thing on the left by py, it wouldn't affect the argmax, and then you would have, by Bayes' rule, p of x given y, meaning you are trying to select the x that's most likely given the observation. In the jointly continuous case, you're going to do the same exact thing, except replace the conditional PMF and marginal PMF with conditional PDF, f of y given x, and f of x, the marginal PDF of x. And again, by Bayes' rule, that's just f of x given y, argmax. Okay, and now in the case where x is discrete and y is continuous, you just write a discrete PMF for x and a conditional PDF for y given x. And in the reverse, if x is continuous and y is discrete, then you would write a conditional PMF for y given x, because that's discrete, and a marginal PDF for x. Okay, just to give you that full range of possibilities. Okay, so where might you use this? Well, one important application of estimation is trying to infer or guess the parameters of a distribution from its samples. Okay, so this is actually where we typically we fit our distributions from data. Okay, so let's say what's happened is we have some kind of experiment that we're running, and we believe that it's well modeled by a binomial. Okay, so let's say that what we're trying to do is determine the parameter x. So usually we're going to call x the thing that we want to know. So in this case, this x is our unknown, and we've observed something we're going to call y. So y is the outcome of our experiment, and let's say that it's binomial and has parameter n, which we know, and parameter x, which is usually p, but here it's our unknown, so we're going to call it x, which we do not know. What is the ML estimator in this case? Well, we have enough information to form the ML estimator, so let's just do it. All right, so what we have to do is write out the conditional PMF of y given x. Since it's binomial, it's n choose y, x to the y, 1 minus x to the n minus y going from 0 up to n. So you see x here plays the role of the parameter p. Okay, and it's 0 otherwise. So then the ML rule will tell us to take the argmax of this conditional PMF. So I'm just going to write that out again. Right, so x has to be between 0 and 1. That's its range because it's a parameter for the probability, which has to be between 0 and 1. And so I just write out the conditional PMF again. And the first thing that I'm going to notice here is that this first term, n choose y, has no x dependence, so I can just drop it from the argmax. So even though its value affects the value of the maximum, it doesn't affect the value of argmax because I'm just looking for the x that attains the maximum value, not what the maximum value is. Okay, and then the next step, I'm going to take the log. So I take the log, I get y log x plus n minus y times log 1 minus x. Okay, and the reason I'm able to do this is that taking the logarithm does not affect the argmax because log is a monotonically increasing function, right? So finding the maximum of the log of something is the same as finding the position where the original object is maximized. So if we're just trying to find the argument, it doesn't matter if we're maximizing the function itself or log of the function, if we just care about the x that hits the maximum. Okay, how do we get the maximum of this function? Well, it turns out that this is one of those nice cases where what we can do is just take the derivative and set it equal to 0. And formally, we have to be a little careful about that, so we can't just go around setting every single derivative to 0 to find maxima or minima. We have to have some properties. So in this case, we're taking advantage of the fact that this is a concave function with respect to x. And so what you can think is that it kind of has this shape. Even though it's always negative, it has, just in this little cartoon, it means that the maximum is kind of attained at this peak here, and that's exactly where the derivative hits 0. So it's basically, it has positive slope, and then it has negative slope, and where it has derivative 0 is exactly the highest value. So I'm going to take the derivative with respect to x of this y log x plus n minus y times log 1 minus x. And I'm going to get y over x minus n minus y over 1 minus x. Set that equal to 0. So I get y over x is equal to n minus y over 1 minus x. Move the denominators to the other side. So y times 1 minus x, n minus y times x. And then just multiply through y minus xy and x minus yx, right? I cross out these two terms, which are the same. So xy is the same as yx. And I'm left with x is equal to y over n. Okay, that is the value of x that attains the maximum. So my ML estimator is y over n. And this makes a lot of sense. So here's the intuition. For the ML rule in this case, or ML estimator, count the number of successes, that's y, in your experiment, and divide by the number of trials. Okay, so if I asked you to take the outcome of a binomial random variable, let's call it y, and to guess the parameter, just given that one observation, this is likely what you would do. You would just take that observation and divide it by the number of trials, and you would take that as your estimate. And now I'm telling you a principled reason for why you might have done that. Okay, let's look at it from a different perspective. So let's say I now also have this prior distribution on x, which I'm just going to write down as 2x from 0 to 1. Okay, and all this means is this is just some particular distribution, and we, in this case, picked it so that the math below in this example works out nicely, but it's just telling you that it's more likely to have higher values of x compared to lower values of x. So we believe, our prior is that we believe x has a higher value, so towards 1. So anyway, what is our map estimator in this case? Well, the first thing to note here is that this is a case where y is a discrete random variable because it's binomial, but x is continuous because it's a parameter between 0 and 1, right? And so I'm going to use the form of the map rule. that takes the argmax, so it's p of y given x, f times f of x. Okay, so I use this form. And then I'm going to just plug in both of those distributions. Okay, so I plug in both distributions, I get n choose y, x to the y, 1 minus x to the n minus y, 2x, right? So I plugged in the prior distribution for x. Okay, so dropping the 2 and the n choose y does not change the location of the maximum, so that's what I'm going to do. Okay, so I'm just going to write out the same thing. I'm going to drop the n choose y, and I'm going to drop the 2 from 2x. Okay, so this whole thing just simplifies to be x to the y plus 1, 1 minus x to the n minus y. And the reason I'm able to do this is that these terms, 2 and n choose y, don't affect the location of the maximum, just the value, and I don't care about the value, I care about the location, the argmax. As before, we're going to take logs. The reason I can take the log is monotonically increasing, so the maximizing value will stay in the same place even though the value will change. So this is basically the same function we had before, but instead of y log x, I have y plus 1 log x. And I'm just going to go through the same exact derivation. Again, this is going to be a concave function in x, and that means what I can do to find the maximum is I can just take the derivative with respect to x and set it equal to 0. That's not something I can do in general, right? So finding the maximum of a function can be a tricky thing, but this is a nice scenario where that just works out. Okay, so we're just going to do that. Set the derivative equal to 0. In fact, we already basically did this. The only change is that we changed y to y plus 1, but let's just go through the whole derivative just to be sure. So I'm just taking the derivative of this function here with respect to x. I get y plus 1 over x minus n minus y over 1 minus x is equal to 0. So I set it to 0. I get y plus 1 over x is equal to n minus y over 1 minus x. Y plus 1 times 1 minus x is equal to n minus y times x. So then opening that up, I get y minus xy plus 1 minus x is equal to nx minus yx. So crossing out the two terms that are the same, I'm left with y plus 1 is equal to n plus 1 times x. So x hits its maximum when it's equal to y plus 1 over n plus 1. And that is my map estimator. All right, so what is this doing? If you look at it, what I'm doing is basically dividing y by n, but I'm just pushing it a little bit towards higher values, really tilting this estimate a little bit towards higher values due to the prior. Okay, and that makes sense because I believe it's going to be higher, so I'm just kind of nudging it a little bit to factor that in given I have limited data. I'm just trying to incorporate my prior into my estimate. So even if I saw 0 successes, I would still report for my map estimate 1 over n plus 1 for my parameter, right? And if I saw n successes, then finally I would report 1. All right. Now, let's ask ourselves some questions about this. So one question we might just ask, well, let's write out the estimator. So I have the ML estimator, which is y over n, and the map estimator, which is y plus 1 over n plus 1. Okay, so I'll just write that out. And maybe the thing I want to know is, are these estimators unbiased? Maybe that's the first thing I want to know, is that on average, do they hit the right value? Okay, well, let's start with the ML. So the average value of the ML estimator is going to be something I'm going to get through the law of total expectation. So I'll take an inner expectation where I condition on x, the value of x, and an outer expectation where I average everything out. All right? So that's the law of total expectation. And the nice thing here is that when I take the average of y, condition on x, now I know the parameter of this binomial y. Okay? So what is the average of a binomial random variable? It's n times p. In this case, x plays the role of p. So what I'm doing in this inner expectation, condition on x, is I'm giving you the parameter x. I'm asking for the average of a binomial divided by n. So I get n times the parameter, in this case x, divided by n, which is the expectation of x. So it's unbiased. It, on average, gives me the correct value. What about the map estimator? Well, I'm going to do the same thing. Okay, so I'm going to condition on x, basically use the law of total expectation. And the reason that I'm going to do that is that that's going to feed the parameter into this estimator. So I now will know the parameter when I'm trying to evaluate this. Okay, so I know this parameter x, I condition on x. And then what that's going to give me is n times the parameter, so nx plus 1 over n plus 1. So it's the form of this estimator where I've replaced y with its average, nx. And so then I just get n over n plus 1 times the average of x, which is just plus 1 over n plus 1. Okay, so this is not unbiased, it's really biased. So it's not on average returning me the average value of x. All right, and so in general, this is just kind of one example. In general, both the ML and MAP estimators are going to be biased, right? So that's just how it is. And in general, it's going to be a little more complicated than that. So here it was nice. I had some nice linear estimates, but in general, they're going to be non-linear functions of y, okay? And it could be quite tricky to identify them, the ML and the MAP estimators. So this was just a special case where we still had to work a little bit, but we got nice estimators in the end, and they happen to be linear functions of y, right? They're just y times some number plus some number, okay? That's it. And in general, that's not going to be the case, all right? So just a little caveat there. So while these estimators are important, so ML and MAP estimators play an important role both in practice and in theory, they are not optimal in the sense that they do not attain the smallest possible mean squared error in general. It's possible for you to find an example where they hit the minimum mean squared error, but in general, that's not what they do. So what you want is the minimum mean square error estimator, MMSE estimator, x hat MMSE of y. That is the one that attains the smallest MSE, and it turns out that it's equal to the conditional expectation of x given y, all right? So that's all it is. This conditional expectation that we've already learned about turns out to be the best possible estimator if your goal is to get the smallest mean squared error, okay? So that's nice. We already know about conditional expectation. All we have to do is use it, and then we're automatically going to get the lowest mean squared error. Why is that the case? Well, if I take the mean squared error, x minus x hat squared, average, and I open it up using the law of total expectation, conditioning on y. So I'm just doing this to show you what happens. Then let's look at this inner term. So the mean squared error conditioned on y. And what I want to do is find the x hat of y that returns the smallest error for every single value of y that I could try. So for every single observation I could have, what is the best possible estimator? Okay, well, let's first open up the square. So I'm going to get x squared minus 2x hat times x plus x hat squared, all conditioned on y. And I'm going to use linearity of expectation to break out those terms. Okay, and because I've conditioned on y, all the terms that depend only on y, basically just x hat of y, those can come outside of the expectation because I've given you the value of y. Okay, in this part, next part, you kind of have to realize to do this. What I'm going to do is add and subtract the same term. So I'm adding and subtracting x conditioned on y squared. Why am I doing this? Well, I'm doing it to complete the square. And you'll see what this means in just a second. So I'm adding these terms, and now these last three terms, so I'm going to leave the first two terms untouched. Okay, these last three terms turn out to be the conditional expectation minus the estimator squared. Okay, so by adding and subtracting this conditional expectation squared, I've created this square minus some other term. Okay, and the interesting thing then is that this is the only term, so this thing in the box is the only term that I actually have any control over. And it hits its minimum of 0 if I choose x hat to be equal to the conditional expectation, and only if I make that choice, right? So any other choice will result in a higher mean squared error for that value of y. So for every value of y, I should just take the conditional expectation. The other two terms that I have sitting outside this box, I can't do anything about them. Those are just going to be there as my error. So what are the properties of this MMSE estimator? Well, remember, one of the first things that we were looking for with the ML and MAP estimators in that example was to check if they're unbiased. And it turns out the MMSE estimator is always unbiased. So its mean is always equal to the true mean of x. Why is that the case? Well, because it's the conditional expectation, when I take the law of total expectation, I just get the average. So that's just a property of the conditional expectation. It also turns out that the error of the MMSE estimator is what we'll call orthogonal. So we've defined this before, but I'm going to remind you, it's orthogonal to any function g of y of the observation. Okay, so the average of the error times any function g of y is equal to 0. So this is kind of a geometric picture of what's going. It's basically saying that there exists no function that can extract any additional information about the residual part of x that you weren't able to estimate any more than the MMSE estimator, right? So basically, on average, you're doing the best possible thing. Okay, and you can see that in terms of this, angle. So you can think of this thing as it being a 90-degree angle to any the error being at 90 degrees to any possible estimator on average. So why is this the case? Let's just look at that. So why would this thing be 0? Well, let's use the law of total expectation. So I'm going to condition this whole thing on y in an inner expectation, right? So what that's going to enable me to do is, well, first thing I'm going to do is just write the MMSE estimator as the conditional expectation, leave the g of y there. And then because I've conditioned on y, I can push that in. So by linearity of expectation, I can push that inward. So I get e of x given y again, and I pull the g of y outside of the expectation because I've given you y. And so I just have conditional expectation minus itself, which is 0. One useful consequence of orthogonality is that you can use it to show things about the mean squared error itself. So you can actually plug in the MMSE estimator as the function itself. And if you use this relationship, you can actually show that the mean squared error for the MMSE estimator is just the second moment of x minus the second moment of the MMSE estimator. Okay, that's just a little thing in case you ever run into it. Let's do an example. Okay, so I'm going to give you this joint PDF, and the joint PDF is going to be some normalization constant. It's 12 over 11, x plus 1, for x ranging from 0 to square root of y, and y between 0 and 1. 0 otherwise. Okay, so the range is not going to be a rectangle. That's clear. So here it is. So I have this function y equals x squared. That delimits one side, and then otherwise I'm bounded by 0 and 1. All right, and what are the map and MMSE estimators in this case? We won't do ML, we'll just do map and MMSE. Okay, so the map estimator is going to be the argmax, okay, of x in its range of the conditional PDF of y given x times the PDF of x. And so that's just going to be the joint PDF, right? Because by the multiplication rule, this thing that I've written is the joint PDF. So I'm just going to plug in the range of x. Here it's 0 up to root y, and I have the joint PDF 12 over 11 x plus 1. So this is just going to be root y, because for higher values of x, I'm going to get a larger value, right? So I just take the highest possible value, that's going to be root y. Okay, so that's the map estimator. The MMSE estimator is going to be the conditional expectation, okay? So that's easy to write down abstractly, but sometimes we have to work to do the integrals. Here's the abstract integral, integrate x times the conditional PDF given y. So in this case, I need to figure out the conditional PDF given y. So I take the joint PDF, I divide it by the marginal PDF of y, which I don't have. So I'm going to have to work that out too. And so that's the next thing I have to obtain. So once I get that, I can kind of go backwards. So I get the marginal PDF of y, I integrate from minus infinity to infinity to take out x. So that means I'm integrating from 0 to root y, because that's where x stops. Okay, so I integrate the joint PDF from 0 to root y, And it turns out that that's going to give me basically half y squared plus, or half x squared plus x. Plugging in root y, I get y plus 2 root y. And that's normalized by 6/11. So I take this whole thing and I plug it in into the denominator, and that's going to give me the conditional PDF. So I get x plus 1 over y plus 2 root y, and then a normalization of just 2, which is 12/11 divided by 6/11. So I'm just going to be left with 2. Okay, so that's where I got this. And so the range is going to be the same as the range of the joint PDF, as we've seen before. Okay, so now I have the conditional PDF. Now I integrate finally with respect to x times this conditional PDF. And this last integral, I'm not going to show you exactly how to work out. It's not too hard. You could just plug it into your favorite symbolic integrator. That's what I did. You get 2y plus 3 root y over 3 root y plus 6. Okay, so you get this nonlinear estimator, and that is the best possible estimator in terms of mean squared error. We're just going to see what the mean squared error is just for comparison. So we're going to just take the map estimator and the MMSE estimator, which we worked out on the previous slide. So I'm just writing down their forms here. So neither of them are linear. Okay, they're both nonlinear functions of y. And I'm going to work out their mean squared error in both cases. Okay, so this just amounts to taking the true value of x, subtracting the x estimator, squaring it, and averaging that. Okay, so I take the true value of x, subtract x hat map, square it, okay? And then I get the integral from minus infinity to infinity twice, and then I get x minus x hat map times the joint PDF dx dy. Okay, so this is still abstract. I need to put in the integration limits. So I'm going to go from 0 to 1 for y and 0 to root y for x. And I'm going to plug in x minus the form of the map estimator, which is root y, the form of the joint PDF, which is 12/11 plus 1, and get, again, using some symbolic integrator, 29/165, which is about 0.18. Okay, so that's my mean squared error there. For the MMSE estimator, I'm going to have to plug in the conditional expectation for the MMSE, which we already worked out. So again, the abstract form of this is just going to be the double integral across x and y, x minus the estimator, the MMSE estimator in this case, squared times the joint PDF dx dy. So I plug in to get the integration limits, 0 to 1 again, 0 to root y, x minus 2y plus 3 root y over 3 root y plus 6. So maybe that's just a little bit annoying. So whole thing squared, 12/11 x plus 1 dx dy. We know we can do this integral. We're just going to plug it into a computer. We get 46/55 minus 64/33 log 3/2, which is about 0.05. Okay, so that's smaller. Okay, that's good. And it turns out because of the properties of the MMSE estimator, this is the smallest possible mean squared error in this setting. So on average, the best you're going to do trying to estimate x from y is going to be this mean squared error level. The last thing I want to tell you is that joint Gaussian random variables or jointly Gaussian random variables are special. Okay, so when you encounter them in the context of estimation, things are quite nice, right? And the reason they're nice is if x and y are jointly Gaussian, then you're always going to know that the MMSE estimator, the best possible estimator, is a linear function of y. Why is that the case? Well, the MMSE estimator is the conditional expectation, and if you remember from before, the conditional expectation is just a linear function of y, right? So it's the mean of x plus the covariance of xy over the variance of y times y minus its mean. We've seen this before. Now I'm using it. I'm using it to tell you that estimation is quite nice for jointly Gaussian random variables. It also turns out, this is something we've seen before, using the properties of the conditional variance for jointly Gaussian random variables, we can write down the mean squared error directly. It's 1 minus the correlation coefficient squared times the variance of x, or the variance of x minus the covariance of x squared divided by the variance of y. It also turns out in the special case, this happens to also be the map estimator. So jointly Gaussian random variables are really nice. because of these properties, we can always just write down what they are using first and second order statistics, which we can usually get either through integration of an abstract PDF, or maybe we have to collect some data. Okay, that's it.